Hello, everyone. Thank you for joining us here at ACE, no matter where you are in the world. And we're very, very excited to have Felipe Petroski such, who is a research engineer, a research scientist at Uber AI Labs. So Felipe is focusing on deep neuroevolution, reinforcement learning, and HPC. Prior to joining the Uber AI Labs, he obtained a BS and MS from RIT, Rochester Institute of Technology, where he developed deep learning architectures for graph applications and ICR, as well as hardware acceleration using FPGAs. So I'm very excited to welcome Felipe to give us a talk today about the paper Generative Teaching Networks. And I would like to let Felipe take it away from here.
All right, thank you, Susan. Thank you very much for the invite, and I'm excited to present. Hopefully, I will do a good enough job for you guys here. So today I'll be talking a little bit on the generative teaching networks, which is a work that I've been doing at Uber AI since about January last year. And the idea here is be able to learn to generate synthetic training data. This work was in collaboration with a few colleagues at Uber AI, namely Aditya, Joel, Ken, and Jeff. Ken and Jeff here actually both acted as co-advisors on this project. If you're interested after the talk, you can actually find our paper as a preprint on archive. Here's the link. And also the code is available on GitHub, and you can play around with it, see what's going on if you're more into a code rather than paper kind of person. Okay, so the main idea behind our paper as a motivation is actually that we saw, especially since 2012 with AlexNet, we see a significant progress being made in several machine learning tasks, but mainly in supervised learning, where iterating over models and architectures and training algorithms and everything over time, we actually see a significant improvement in performance that is both powerful around with it in terms of like how the accuracy is improvement, but it's actually very interesting how these things are evolving over time, because things that some might think are very small changes to these architectures actually have significant changes in terms of like the final accuracy, right? So we're very inspired by this ability to iterate over architectures and eventually obtain significant performance in terms of how these architectures can perform on real world tasks, right? And including eventually passing human capabilities over time. But the main issue we've seen is that although we can see this significant progress when we iterate over these models, most of the knowledge that we gather from strictly on the architecture itself tends to be not shared over iterations. So we kind of just throw it away. We take like 10 architectures. Each one of them is trained from scratch. Although we tune hyperparameters and things like that, most of the knowledge is kind of thrown away, right? And you can actually see the image on the bottom right is actually an internal tool that we use at Uber for tuning. So you can actually see, well, I guess not much to see there, but beyond we iterate over these models, but in reality, the only thing that each one of these models becomes is just a parameter configuration and then just a performance that we try optimizing. But eventually, most tuning and search tends to have diminishing returns. So we quickly hit a ceiling whenever we're trying to do this search. But from our perspective, I guess the main issue is this issue of sharing information, right? So like being able to, I guess, every time we train an architecture, how can we actually leverage information that we gained during this process so we can train future architectures faster, right? Rather than having to train 1,000 architectures as if we never trained an architecture in the past. So that's really the motivation to our approach, and I'll go a little bit into detail a little bit more later. But I guess the main goal here is how we could actually decrease the iteration costs if we know that we're going to be training a large number of networks, right? We don't want to optimize how fast we can train one network. We want to optimize how fast we can train a large number of networks, right? If you're going to do things like, if you have a new problem that we need to solve, you're not going to just train one network and deploy that network. You're going to go through many iterations and trying to find the best network that you can for this particular problem. So before I can go into detail into our approach, I wanted to give this anecdote on how humans learn and see if that actually, maybe that resonates with you guys. So let's see. So in terms of how humans learn, you can actually just, think about it a little bit. So humans learn in many ways, right? Practicing, sorry, is one of the main ways we've learned. So, we want to, play basketball, so we kind of just go play basketball, and we try until we're good at it, or we just oh well, we're mediocre at it, so let's call it here. We can also learn through reading, for example, right? So you can actually, this is quite interesting to me, because you can actually use a skill that you've learned in the past, which is to read English, and use that skill to learn about some other skill, let's say practicing medicine, which is completely unrelated in this case. So you're actually performing reading, but in reality, the thing that you're practicing or learning about is something completely different, which is quite interesting. So that's another way that we can learn. And also we can learn through observation, right? So we see other people or even animals or machines doing things, and we can actually understand their goals. We can understand the step-by-step that they're going through to achieve these tasks, and we can imitate, and we can actually learn from this process, right? So all of these mechanisms are different in their own ways. They're applied in different situations, but they're all very interesting learning mechanisms that we don't really use in machine learning that often, right? But I guess the core component of all of these methods, and the thing that we keyed on and were motivated by, was this idea that the learning mechanism on its own is actually evolved and learned over time, right? So like I mentioned with the reading, in this case, the learning process was actually something that we learned in early age. So it's actually quite interesting, because the learning process here is being tuned over time. So we get a better practice routine. So if you're a basketball coach, you find better routines that you can apply and get your athletes to perform better. You can actually revise your books. So you can rewrite things so that they're easier to understand. I can completely revise my slides until we're hopefully happy with what we got. And we can actually teachers themselves actually optimize their methods, right? So the very first day that they taught a class is probably significantly different than the way they teach a class 20 years later, and the things tend to improve over time. So this is quite interesting, right? Because it's very different from the way we do machine learning in general, because although each student kind of learns separately, the underlying training mechanism, or the teaching mechanism, if you say, is actually shared across all of them, and is tuned over time, not just over the teacher's time, but is actually tuned over, I guess, our whole civilization, right? So teaching now is probably done significantly different than it was done 2,000 years ago, for the better, for the worse, but it's been evolving and being changed over time. So now that we have, I guess, a little bit of background and what we had in mind, let me go through a little bit on generative teaching networks, which is our way of attempting to solve this particular problem, or working towards this ability to learn a large number of architectures. So to be able to do this, we're actually going to focus specifically on accelerating neural architecture search. And for this, the first task that we wanted to do is create effective training data, right? So if we're going to be teaching a large number of architectures, we need training data that can effectively teach those networks. Once we can get the training data, we will basically estimate the performance of a large number of architectures. So we're going to sample hundreds of architectures and just estimate how each one of them can perform, kind of like a student doing mock tests and SATs kind of thing, and seeing how well they can perform on a particular task, right? And then after we do this procedure, we're going to pick the best architecture with, or the architecture that we estimate is the best, and we're going to basically just do our best in training that network. So what that means for us is just training for a really long time, or with a lot of data if you have more data, and see how well that architecture can perform under more canonical conditions. So that's really the process that we're going to go through in accelerating your architecture search. So GTNs, which is the target of our paper, is going to be focusing on step one, which is how can we actually create this effective training data to teaching these architectures, right? So for GTNs, we're going to generate data, right? So and the idea is we're going to generate data that never seen before learner. So like, architecture we've never seen before. It's randomly initialized with weights that we've never seen before. And we're going to train on the data that we generated to perform well on a specific task, right? So let's just use image classification as an example, like MNIST. It's easy to think about. And the idea is, how can we actually generate MNIST-like data, maybe, that can teach a learner how MNIST images can be classified, right? And the way we do this is through this nested optimization system, where basically in the inner loop, we optimize learners on the data that we generated. And then on the outer loop, after we've trained this learner, or let's say over 32 steps on the generated data, we check the performance of the learner on real data, MNIST data, and then we can actually optimize the generator parameters based on how well the learners perform in the future, or like, after training on the real data, on MNIST data. So this process is very similar to just meta learning in general, and is our MAML, if you're familiar with that, in this idea that I guess there's an inner iteration where it's basically an optimization step, in this case, that has no samples coming from the real task that we care about, but the outer loop is set up in a way where the parameters of the generator are optimized such that learners can perform well on MNIST tasks, for example, right? Hopefully that.
Felipe? There was two quick questions here, if you don't mind.
Of course.
The first one,
this is somewhat complicated, so I hope I get questions here, because we want to make sure that everyone understands a little bit. So yeah, go for it.
Awesome, thank you. The first one is, does the learner only, let's say the learner is doing like learning, like updating, is it only after a new iteration of the generator is created? So I guess the question is more like, can the generator and learner be trained in parallel, or is the generator trained first in one, sequentially?
Yeah. So the idea is we only have one generator, right? So the generator's lifetime is pretty much like eternal, the whole process. The learners themselves only live for a few iterations. So how many iterations we're going to train them on the generated data, and then they're thrown away. Of course, you can actually do a little bit more on the simultaneous optimization if you want. It's going to look a little bit more like truncated gradients if you do it that way. If you do it that way, it could be problematic, because if your generator is only teaching one single learner, then the process kind of like gets simplified into only having a learner, and the generator doesn't really do anything. So this process really requires having a number of learners. That number could be 10, it could be 1,000. It's hard to say. But you do really need several learners being optimized by the generator, or optimizing on the generator data. So yeah, I guess I'm not sure that answers the question there, but
yeah, I think that it does. And the second question was, but I guess it's more clear now that you have described that again. So the learner does not actually use the real data, but rather only the data from the generator.
Exactly. So the parameters of the learner actually are never optimized on the real task that we care about. It's only tested on that. And the reason we have to test it on that is because after, let's say, 30 steps of training data on the synthetic data, there's actually a dependency on, so like the final parameters of the learner depend on the parameters of the generator, which means if we compute the loss of the final learner on real data, we can actually compute gradients all the way back to the parameters of the generator. That's how the process works. But then after we actually compute the loss on the real task, we throw the learner away, sample a new one, and start the next iteration.
Gotcha. And there was one more question, but feel free to go through it if it's in a future slide. So what are the metrics for evaluating the learner performance? What is the meta cost function?
Okay, so the meta cost function is, I guess, up to or depending on the task, right? So if you're doing things like image classification, the meta loss, that language might be easier to think about here. The meta loss is really just the cross entropy, I guess, softmax that you usually use for logistic regression, right? So it's really domain specific. So it's not so much depending on the GTN. The inner loop loss, on the other hand, can actually be separate, right? So like in reality, when we're teaching about MNIST images, we might not actually use logistic regression as our task. We could actually use pretty much any other loss, as long as the format, or I guess the shape of the inputs and outputs match. So as long as your task in the inner loop, as long as your task matches the format of the architecture, you can use whatever you want. If you want to use regular regression instead of logistic regression, reinforcement learning, whatever you want, it works. The meta loss in the end depends on the specific domain. So if you want to do image classification, logistic regression, if you want to do reinforcement learning, there's plenty of options that you can choose from, but the two are independent.
Gotcha. Thank you.
Yep. All right. So hopefully we kind of understand how this process works. This is actually more complicated to implement than it is to, I guess, visualize. And hopefully, if you guys want to refer to the code actually makes it a little clearer on what's going on when we actually do these things. But this type of process is fully supported with both TensorFlow and PyTorch, although our implementation is in PyTorch in this case. Okay, so just a little bit of related work. I don't want to go too much into details exactly what each one of these is doing, but it's quite interesting. So McLaurin in 2015 actually had this paper called Hypergradients, which hopefully some of you are familiar with. But he actually showed that the gradient descent process itself is differentiable, and that, for example, if you're trying to train images on MNIST, you can actually the whole process itself is differentiable, right? The learning rate, the initialization parameters, the weights, the initialization weights, I guess, and even the synthetic images are actually differentiable. So it was a very interesting paper, and they actually have a very small toy example where images, the training images themselves were actually trained to be able to teach networks how to perform well on MNIST. The Wang et al. In 2018 actually explored this a little bit more. This was in parallel with when we were actually starting our own exploration of GTNs, but he showed that we can actually train the data directly to and get pretty good performance on tasks like MNIST and Cypher10, even when the learner is actually changed over time or reinitialized over time. We've seen in the past that we can actually create more effective training data. For example, Graves et al. 2017 showed with curriculum learning that we can actually leverage information about samples that were used like in the past to inform how we should actually sample samples in the future. So basically, instead of just independently sampling images over time, you can actually perform a curricula that can better train these architectures than just the IAD version. So it's quite interesting that simply rearranging the order of images can actually perform a significantly better training. And Fen et al. In 2018 actually had this very interesting paper called "Learning to Teach," which is very close to our approach here. But on their case, the idea is the training process itself, like hypergradients, is trainable. But on their case, the approach that they took is actually on the subsampling of mini batches. So rather than ordering samples as they come in, you basically can have a large mini batch IAD sampled from the full data set, and then just subsampling those images into a smaller set that can be more effective for training. And they show that actually has some improvement over time. So it's quite interesting that we see that not only order in terms of how these batches are presented matters, but we actually also see that the samples that are presented within any one batch is important, and is any effect that you can have in this training data can significantly improve your performance. So this is great. We wanted to see we have this great new approach. We wanted to try it out. Unfortunately, for the first months or so that we were trying this, the plot that you see here is pretty much the only thing that we were looking at, where we were training these generators to perform to teach learners, but the learners eventually always kind of just lose all of the information. So eventually, the whole problem becomes unstable, and all of the images kind of like all of the information that we've gained kind of goes away, and our performance degrades over time. This is very unfortunate, and we weren't able to achieve remotely close to state-of-the-art performance with this instability problem. The way we fixed this.
Sorry, real quick question.
Yeah.
For this graph, is it across only one single learner?
No, actually here, I probably should have been more explicit. Each point in this line is actually a different learner. And what you see here is actually a meta iteration. I probably should have changed the X label here, but it's actually a meta iteration. So these are basically how well the generator itself is able to teach. So it's the performance of the learner after the final training step on the generator data.
I see. Oh, and I guess this ties into a question that was asked kind of related to this, but also to one of the previous slides. So if you keep learner architecture fixed, or if you do that, whether you do that or you do not do that, you can clarify, then the generator learns better synthetic data, correct?
Yeah, that would be the intuition. And we do that, I think up until the slides, I actually don't remember if for this particular plot we actually did that. But in general, our approach, we sample many architectures, and for each one architecture, we actually sample the weights randomly too. The more generalization, the more you change the architectures, the better generalization you're going to have. But at the same time, there's a trade-off, because if any architecture could be sampled, then your generator cannot let's say, specialize into training a family of architectures, right? So there's a trade-off, obviously. It will be better for generalization, but it can be worse because of specialization, right?
I see. So I guess you can think of the learner as one kind of lever, like changing up the learner, and the other lever is kind of the generator that generates synthetic data.
I'm not sure I follow. I guess the lever.
Right. So I guess if you want if you're changing the architecture a lot, then you won't be able to, like, the generator might, not be able to produce all the best images. Is that?
Yeah. So I guess it's the same. You'd see everywhere, right? So like, if you only have to teach a set of students, a specific set of students, you can actually tailor your curricula to be able to teach this particular set of students, right? But if you have to teach any students, or any architecture you could ever see, then you can't specialize so much, but you might have better generalization capabilities, right? So it's a trade-off. We don't know how much we actually are specializing to these architectures yet. Although I have a slide later on where we actually have a significantly large range of architectures that are being sampled.
Gotcha. Thank you.
Okay. So where was I? Okay. So the instability problem. This problem just comes pretty often in deep learning, especially when you start having very large computational graphs. So like architectures like ResNet or LXNet, the larger the architectures are, the more unstable they tend to be if you don't use things like batch normalization, right? So it's a recurring theme. Things like LSTM try to fix that. Things like pretty much any type of normalization scheme tends to help with that. In our case, we're not so different than the very large architecture being normalized, or the very large architecture with exploding or vanishing gradients. What we see is that basically, as we're training the GTN, the computational graph in our case is actually the parameters of the weight, the learner, being optimized and changed over time, right? So the issue in our case is that between two iterations of a learner, there was no normalization step. So the weights of the learner could actually become unstable, especially with training algorithms like Adam, right? So the weights of the learner can actually start changing significantly over time, and we were actually seeing that causes exploding and vanishing gradients over time. So the way we fix that is, taking inspiration from LSTMs and batch normalization is by actually using weight normalization. Because if you think about this process as a weird recurring network where the states of the network are actually the weights of the learner, the weights of the learner would actually have to be normalized, not just the activations of the learner, right? And this is actually a pretty simple process. The way you can do this is by reparameterizing the weights of the learner with this simple formulation here, where we just compute G and V, or we keep track of G and V instead, and we can compute the weights of the learner through that process. Just performing this simple switch from the weights representation significantly improves the stability of our process, as you can see on this plots. So basically, before, almost none of the parameters that we could find, the hyperparameters that we could get, were able to train for long periods of time, or even to great performance. But with rate normalization, pretty much the whole process is extremely stable, and it was actually hard for us to break it to some extent. But the great benefit of this is we can train for a long time and actually achieve, I guess, close to state of the art, or I don't know, state of the art for MNIST becomes a real metric at this point, but we get close to the 98-99% that we can get on MNIST using this approach. So this is for us, it was actually very enlightening. It was kind of like a eureka moment when we found this. We actually think that applying weight normalization to pretty much any meta learning method, MAMO, or pretty much any other method that relies on second order gradients would actually be beneficial for stability purposes. So we're actually pretty interested in seeing how that plays out in future work.
Nice. Okay, we do have one quick question here. There's so much interest in this topic. So was the weight initialization here better than, let's say, the warm starts for learner architectures or pre-trained learners like AlexNet or ResNet?
We don't use any type of warm starts. We actually just do random initialization using just Xavier initialization, so just pretty standard. We don't even learn the parameters of the initialization itself, although that can be optimized over time too if we wanted to. But we didn't really see that much benefit on changing how the initialization done, because there's probably interaction between how the initialization and how the optimization process works. But if you actually tune one or the other, you probably can actually get the same effect. So tuning both, you probably don't gain much. And sorry, I don't know if that actually answers the question, or if the question was a little on that.
I think that's good. Thank you.
Yeah. Okay. Let's see. Okay, so after weight normalization success, we actually see a plot that everyone wants to see. That it's something that is just like curve moving up, that eventually gets or maybe plateaus, but it gets close to the performance that we want and care about. Interestingly, the images that we get from this training process actually look like this, which some might expect, some might not, but in general, the images are pretty alien looking. I don't want to say unrealistic, because we can actually, I'm not sure if you guys can see my mouse here, but you can definitely see digits, and you can see features of digits in most of these images. But perhaps the more interesting effect that we see is that early on in the training, we see significantly more abstract images than later on in the training. So as you can see on the right, the images tend to be a lot more realistic as they get close to the end of training. And this is not something that is tied to the number of iterations. So if you actually increase the number of iterations that of the number of samples that we generate, the more samples we generate, this kind of effect tends to just be on the last, let's say, 10% of iterations, rather than at the 32nd iteration in this case. So it's actually something that is tied to the overall training curricula, rather than just fixed number of steps, which is quite interesting. we can have a very long discussion in how or why these images look like this towards the end. But I think we can spend pretty much too much time talking about this. So I'm gonna defer this to the very end, unless anyone has any specific questions right now.
Right. There's like a quick question: is there a pattern between the nature of the synthetic data and the learner architecture as they happen?
Probably. I think that would be interesting to see. We found that depending on the architecture, the images tend to look different ways. Interestingly, when we actually worked with MLPs instead of like convolutional networks, the images were a little bit more realistic. But that could actually be more from the architectures being very simple rather than being an MLP versus a convolutional network. Anyway, the way the images look surely depends on how the learner architectures or the architectures for the learners are actually sampled. But it's hard to say if the way the reason they look like this is because different architectures actually really need different images, or is it because the different architectures have different gradients, I guess. So the gradients that we obtain from the system is different, and therefore we get different images, right? So like, I guess the question is, do the images look like this because they need to look like this for these architectures, or do they look like this because drifting and I guess noise in the gradients actually kind of force them to look like this, right? So it's hard to say where the effect is coming from, although we do see that different architectures result in different looking images.
Gotcha. Thanks.
Okay, so this is very interesting to us. We spent several meetings, I guess, discussing how these images, why these images look like this, and like how can we make them better if we wanted to make them better, or if we don't want to make them better, like trying to understand why they look like this. And I guess we can talk a lot about this a little bit more towards the end. So, okay, now that we have actually successfully, trained these synthetic images, or the generator for these synthetic images, we wanted to see how well we actually perform against or compared to, real data, for example. For this system, we wanted to see apples to apples, how well we perform. So rather than just training a large number of architectures with fixed hyperparameters, we actually went through the process of using Bayesian optimization to find amazing hyperparameters to train on real data, as well as a meta-learning, kind of like Maclaurin style, to optimize the learning rate, initialization parameters, and pretty much any parameters that we could think of on the optimization, the inner loop optimization, to see how fast we can actually train these networks using real data versus synthetic data. So the plot on the right, you can actually see that with a fixed number of iterations, so 32 iterations in this case, we can actually get better performance if you use synthetic images, which is the red line, as opposed to just using realistic images or images coming from the MNIST data set. And interestingly, if you actually tried optimizing the pixels of the images directly rather than using a generator like we do, you would actually get the green line, or the data set distillation line here, where the performance, it's improved over time, but it never really matches the generator performance. And this could be actually from either a generalization effect. So the generator is actually forming some type of regularization on the images, or even just a form of maybe the generator just makes it a lot easier to train these networks, right? So it's hard to say exactly where the improvement is coming from, but you do see a significant improvement from using a generator rather than just trying to optimize, pixels directly. And if you actually, take the final generated images and actually plotted performance of a final learner over time, you actually get the plot on the bottom right. So you can actually see that it's not just the final performance after 32 steps that is really high. It's actually the learner over time is trained significantly faster than when we were training on real data. So you can actually see that after about, I think it was 14 steps or so, we already get 98.5 here accuracy on MNIST. And 15 steps, or about 15 steps of inner loop iterations actually is only 1,500 images of training. So each image is only seen once. So it's quite interesting that we can actually get this high accuracy using just vanilla training on 1,500 images, as opposed to, I guess, the full data set is about 50,000 images, right? So the training is actually significantly condensed as compared to just regular training on these images. We actually, although MNIST is great, the results are great. We don't want to stay with MNIST because I guess it's still considered kind of like a toy image. So we actually show that the same effect is happening on Cypher 10, although, to some, Cypher 10 is also a toy image or a toy problem, but we actually see the same effect, although it's probably not as exciting because the final accuracy is not close to the 98% accuracy, but we do see a significant improvement in terms of speed on how fast we can train these networks to a certain accuracy, right? So if you were to fix the number of iterations to 128 steps, the accuracy you get with the synthetic images is much higher. Or if you want to actually think about it in a different way, to get the same accuracy, it's actually significantly faster if you use synthetic data. And in our case, it was actually about 4 times faster. And this is actually 4 times faster than the best ever hyperparameters that we could get, not just the vanilla training. And these hyperparameters are very well tuned. In our case, the 4 times faster than real data was actually the real data here is about 4 times faster than the default hyperparameters that you'd get if you're just doing Cypher 10 training as with TensorFlow or PyTorch. So it's quite interesting. It's very effective, as you can see that we can actually train any one architecture significantly faster. But just like on MNIST, we actually see images that look like this. And actually, on this case, it probably look a little bit worse even. So if you're familiar with Cypher 10, these images are supposed to be things like trucks, cars, boats, some animals, I think. But in reality, I don't see pretty much any features that could lead me to recognizing these images here. So it's very interesting here. We see this effect is a lot more amplified on Cypher 10, but it's hard to say why. We actually think in this case is simply because we weren't able to get the 95% accuracy on Cypher 10. Or the alternative is these images could actually be some type of adversarial training data. So the more, the more dimensions your images have, I guess in this case they're RGB, they're slightly larger than the MNIST case. The more dimensions you have, the harder it is for the images to look realistic, simply because I guess there's some type of adversarial training happening with these images. Although again, it's very hard to, I guess, identify exactly where the source of alienness of these images is coming from. Okay, so great. We showed that we can actually train a large number of architectures, which is, on its own not very useful. So how we actually make this whole approach useful in general is applying it to accelerating architecture search, right? So remember from the beginning of the presentation, the motivation was, if we take a new problem, we're not going to train one network, right? We're going to train a large number of networks. We're going to explore architectures. We're going to explore hyperparameters. So how can we actually train these architectures better and faster? So now that we have this ability to create a curricula that can easily and it can faster train these architectures, we're actually going to go through the process of training a large number of architectures and seeing if we can actually identify the best one using this process. So the search space that we're going to be using for our experiments, we use the conventional microarchitecture search NAS search space. On this case, we basically have a template of what a convolutional network may look like. In this case, it just has normal cells and reduction cells. And the idea is to search over graphs of computation graphs within these cells that can describe how the computation will be done over the architecture, right? So we search over things like, convolutions, separable convolutions, pooling, average pooling, and basically how these computations are connected with each other. So this is the search space. We don't really modify or play too much into being able to sample or optimize these architectures over time. We just need to know, I guess, that this is the search space that we're dealing with for our particular use case. So I guess for the GTNs, what we're going to do is we're going to basically, before we can actually run the full architecture search, we wanted to see how correlated our estimates of the performance are with the actual real performance, right? So if you think about it, although we can actually train the performance of these architectures faster, the final performance might not be correlated with how well these architectures would do had we trained them on real data, right? So we need to be able to measure how correlated these two metrics are. So the way we did this is by we sampled 100 architectures from that search space randomly, and then we basically trained these architectures, each architecture twice. Once we train it on the real data, like we would if we were just doing random search, architecture search. And we trained it for a long time, 100 epochs, I guess, in this case, is what we define a long time. And that gives us a estimate of the performance of this architecture, right? And this will be the y-axis on this plot. And the second training that we apply for each one of these architectures is actually using the GTN data. So we basically take each architecture, train it on a very small training regime with 128 steps. So this is actually very quick. It takes a few seconds per architecture. And then we evaluate that architecture on the same validation set from, I guess, Cypher 10 on this case, to see how well that architecture can do after training on synthetic data. And this is actually the x-axis here. As you can see, the performance is actually significantly worse for most architectures, or pretty much every architecture, although I guess the training is significantly cheaper here, right? So obtaining the Y value for each architecture takes, I think it was 4 hours or so a few hours. But getting an estimate of the x-axis here takes about 5 to 10 seconds for each architecture, depending on the architecture. So it's an estimate. It's a bad estimate, depending on how you look at it, but it's a very cheap estimate of the performance, right? And it's quite interesting because if you actually see the highlighted architectures here on the top right, those are the top 10 architectures. And they're actually highly correlated in terms of how they perform on GTN versus how they perform on real data, right? And that's really all we care about. We don't care about correctly ranking every architecture. We just care that if we were to train a large number of architectures and get an estimate of their performance, we can actually accurately or approximately pick the best architecture well. And if you actually see the correlation that we get from using GTN, from training with GTN for 128 steps is actually equivalent to the correlation that you'd get if you train for about 1,200 steps on real data. So it's about 9x actually more effective for estimating how well this architecture would have done if you train it for a really long time. So I guess in our case, like I mentioned, we don't care that we can actually match the final performance. We just care that we can actually get an estimate or the estimate of the rank of these architectures more effectively than we could if we were to use the real data.
I see. A really quick question here. Yeah. So you do this like really quick training just to get an estimation of how would it perform well after you train for a long time, but you don't actually train it for a long time, and the cutoff time has nothing to do with whether it starts to converge or not.
No, yeah, that's exactly right. Here on this case, we trained each architecture twice because this was just like I guess, correlation experiment. This is not a full architecture search experiment. This is just a correlation test to see if the two metrics are correlated, right? But in both cases, we trained for a fixed number of steps. I guess on the y-axis, which is on the real data, we train it for 100 epochs, and on the x-axis is for 128 steps.
Gotcha. Thank you.
Yeah. So, okay, this is great. We know that it's correlated. We know that if we picked the best architecture, it's kind of highly correlated with the real data. but that's still not a full architecture search. We want to see, had we trained a large number of architectures with GTN and we picked the best one, how well would have the best one performed if we trained it for a really long time? Like, I guess in this case, a really long time is like 600 epochs. This is very standard in the new architecture search, like literature, where we have a surrogate or a proxy estimate for how well these architectures would do, and then once we find the best architecture, we actually enlarge the architecture training for as long as we can, with a lot of samples, and see how like the best possible scenario for this one architecture, right? So we went through the exercises of training the GTN, sampling 800 architectures in our case, and then picking the best one and training it for a really, really long time. And we actually saw that our method, if you hold everything else constant, in this case, everything else is how the architectures are sampled. So every one of these algorithms actually just sampled architectures from the search space randomly, and then just changed how they get an estimate of the final performance, right? You actually see that our method performed quite competitively here. And in our case, it was cheap to some extent. So it was about 16 hours of GPU time, where the 16 hours were split in two, where 8 hours were used to train the synthetic data, and then 8 hours were used to actually train the learners, and 800 learners, and then pick the best one. Obviously, future work might actually see that there's better trade-offs here, or actually doing it online rather than just like in these two steps. But we didn't want to spend too much time, I guess, exploring this particular portion. We just wanted to actually show that doing this is actually an effective way of getting an estimate of the performance of these architectures. So, in general, I guess these were successful, and we actually show that we can use synthetic data to accelerate architecture search in our case. So for future work, we wanted to actually explore a little bit more into like other domains. So although Cypher 10 is better than MNIST, we still want to see like, larger problems, more, I guess, closer to what real world problems look like. For example, ImageNet. We also wanted to see how other domains altogether actually look like for recurrent cells, for example, because it's quite interesting, because you can actually get, you have a lot more flexibility on how the training mechanism happens, because there are things like hidden states, and the architectures are a lot more interesting. So we see a lot of potential for future work in the, I guess, recurrent domain, or the problem set that have recurrent cells as a solution, right? We actually have interest on reinforcement learning too. We had a little bit on example of how that could be done in our supplemental material, although it's still just an exploration of how this would actually be done to accelerate reinforcement learning specifically. Yeah, and just for interest of time, I guess I can just quickly go through this, but like, we're also interested in on having closed loop teaching, right? So like in our case, when we generated the curricula is fixed for everyone, but you could also imagine a way that the generator actually has the output of the learner as an input. So basically, the next sample depends on how the learner was performing on the previous batch, right? So it's quite interesting. Maybe that would actually result on curricula that are adapted per learner and have better performance, because we can actually have a generator that tailors to the specific learners, right? And finally, we'd also be interested in trying things like optimizing the full process, right? So like optimizing initializations, optimizing the update rules. So, maybe we don't want to use SGD or Atom. We actually want to create our own, or even the loss function itself if you don't want to use logistic regression, right? Because like in reality, every one of these systems can actually be parameterized. And if it's parameterized and differentiable, we can actually optimize along with the generator, along with the rest of the process, right? So just to finish up here, so we actually showed that GTNs can create synthetic training data that is both more effective than the original data for training, and is also agnostic to the learners, right? So when we actually do this architecture search, these 800 architectures that we've trained were never seen before, but we're still able to teach them effectively and efficiently. But the images don't look realistic at all. They don't resemble directly what the original data looks like. And once you connect, when you can create synthetic training data or effective training data, you can actually use it to create a competitive architecture search algorithm, like we showed with our NAS results. Okay, so that's it. Hope you guys liked it. I'll be here for a few questions and I guess discussion, but I hope you guys enjoyed the talk.
Awesome. Thank you so much. And actually, the comment section is, there's a lot of people talking about like comparing it to maybe generator networks. I just wanted to like ask one or two questions, and then I'll combine the other questions on the kind of GAN discussion together. So the first one is from Ali. So he mentions with the higher accuracy, I guess when you mentioned that when it's the learner is learning, I guess, and then it achieves high accuracy, is there a possibility that it's due to overfitting? And I think we had discussed a bit before the going live about how it kind of goes from underfitting to perhaps overfitting. Like, could this be related to that?
Is that related to, sorry, is this asking about, I guess, the way the images look like on this slide?
I think it's the performance, the accuracy from the learner. Yeah, I think this.
No, I don't think it actually goes from underfitting to, wait, sorry, can you repeat the question?
Oh yeah, sorry. Is it possible that the higher accuracy is achieved through overfitting?
No, probably not. Because these are actually the accuracy on the test set. So the images that we're getting computing the accuracy here were never seen before. They were not seen by the learner, but they were actually not used to train the generator either. So these images are never seen before. And the learner here has never even seen an MNIST sample before we actually measure the test accuracy here. So I guess I'm not sure if that's the question, but it's not overfitting, I guess, in the classical, like the normal interpretation.
Gotcha. Yeah, I think that's a good distinction to make. I spent a lot of time just trying to get back to that slide.
Yeah, especially because we have the synthetic data, but MNIST data also is split into 3 data sets. So in reality, we have 4 data sets: synthetic, training, validation, and test. So it's fair to misunderstand or to like miss which one is being used at which point.
Yeah, exactly. A question, do you think that the lack of realism in the CFAR10 images is due to not saturating the image generator performance?
So yeah, that was actually one of our interpretations of it, or hypotheses. So the reason we actually believe that is because we worked on this for several months, right? And especially on the MNIST images, the more I worked on this, the better images we were getting over time, especially towards the end of training. So we actually saw that the better the generator, the better the more effective it got, the better it was, the more realistic the images were looking. So we actually see that it could actually be a matter of like, we can't optimize the generator well enough to get the final images that we care about, right? So that's definitely one of our strongest intuitions on why, specifically on the CIFAR10 images, why they looked that way.
Gotcha. And because there were some comparisons to, I guess, GANs and whatnot, one comment actually was that, I'm trying to find it. So does this seem like it's GANs, but not for a specific task? Rather, we have multiple classifiers, I guess, as opposed to like the typical critic network.
It's hard to compare the two, because in reality, if you think about GANs, yes, there's a single architecture, but that's not the only difference, right? The training process is very different than GANs. With GANs, the classifier is trained to predict if the image is real or not, versus in our case, the classifier is trained to be able to predict the label for the generated images. So it's basically just trained on those images. But the generator is actually trained on the second order gradients. So the whole training process is actually significantly different. The only thing that they share in common is that they both have a generator, right? So they both have an architecture that goes from a latent space into a image space. But beyond that, it's kind of hard to say how they relate, because there's not really a lot of overlap there. We had some experiments to see if we were to train on images from a generator, like from a GAN generator, if those images would actually be more effective, which, you could argue that would be the case because the generator shares similarity with the learners because they're convolutional networks too. But in reality, we actually saw significantly a degradation in performance. So the generator is actually significantly worse for teaching than the real images, as opposed to our case.
I see. Yeah, actually, you just predicted one of the next questions, which someone literally have asked, did you compare it to GAN-based data augmentation techniques? And you just...
Yeah. So we did, and like, I guess, the argument on why that would actually could be more effective is on the architecture, where we actually saw that the performance was actually significantly worse. So in general, the final accuracy was worse with GANs, and also you actually usually take significantly more iterations to be able to do so.
I see. Yeah, there was like a question where they were wondering if Uber is interested into this to generate urban scene images to accelerate the training of their cars.
I guess my response can come in two sections here. I'm part of Uber AI, which is separate from the Uber ATG unit, which is the self-driving vehicles portion. So I guess from my perspective, I'm not specifically focused on, I guess, self-driving. Although we have other computer vision problems at Uber that do not involve self-driving. So in our case, it's not about generating I guess training data for, like, to be able to generalize better. In our case, it was actually be able to do architecture search better, which, ATG is an obvious potential customer, but it was actually not directed at ATG on this case.
Gotcha. Yeah, that makes sense. I think they were just having some fun with that question as well. Yep. For sure. I'm just going to see some more questions. Actually, let me ask them some clarifications.
No problem.
Right. There was a comment / questions on they were just wondering what the adversarial robustness of the data, which I assume they mean the data from the generator, is, because it could be easy to fool networks with like a pixel off on original images. So could that cause any issues or problems here?
We didn't look too much into that, although it's definitely a very interesting question. So in our case, the final networks that are being deployed are not actually trained on these synthetic images, right? So like these images are only used to select the final architecture, but they're not used to train the final architecture, right? So in the end, it's hard to say where the effect would come from. One thing that we could see is that the estimates that we're getting could be biased towards architectures that are more susceptible to adversarial attacks, although that's probably more future work. It would be very complicated to actually be able to measure that. But I guess in our case, we don't really care too much about, I guess, if the network is more susceptible after training GTN data. The only way we would actually would rely on that is, or care about that, is if somehow the GTNs are actually biasing the search to architectures that are more or less susceptible to the adversarial attacks.
Awesome. Okay, I think just one last question in interest of time. Could an interpretation of the imperfect images be that if they're in some latent space, that kind of magically helps with the classification task?
So that's one potential way. We actually have three interpretations, or three different ways we could actually see these images, right? So one of them is these images are actually unrealistic because they are better, right? So like the optimization process actually forces them to be unrealistic. And you can actually think about it in a way of like either regularization. So the kind of like it's injecting noise into the images so that the classifiers don't overfit to them, or even just from a better maybe synthetic good training data might not be realistic, right? So if you think about it, presenting one image of a time of zeros and ones might not be the most effective way. Maybe you want to actually create like an image with like 100 zeros kind of like morphed into one, or even just separate into one image. So perhaps effective data doesn't actually look like real data, because you can actually get more freedom with it and have a lot more effects with it, either from a generalization or from a regularization perspective. The second interpretation is it could actually hurt, right? So maybe it actually hurts to have these unrealistic images, but our training process or our optimization process does not allow us to actually find the great training images that actually look real, right? So maybe we just haven't gotten there yet. So that could be definitely true, especially because we're using SGD, we're using Atom. The whole process is kind of like stochastic by nature, and it's hard to say if we've reached the global optima, right? So maybe there's actually a better search space or a better set of images that we just haven't found yet. And the third interpretation is actually maybe they don't matter, right? Maybe it's actually being realistic and being effective for training is just independent. But the reason they look this way is basically drift causes them to fall in a space where most of them are realistic. And then if you actually think about it in a way of, if you were to sample from a very large space, you're very likely that you're going to pick an image that is unrealistic, but every so often you're going to find one that is realistic. So it's hard to say which way is the correct one, right? So like from our perspective, all three of them are possible, but I guess it either hurts, it either helps, or it could actually be nothing, and we're just looking at drift that just happens over because it's a stochastic process, right?
Gotcha. Thank you so much, Felipe, today. And thanks for that really awesome summary at the end of your three kind of ideas about this. Thanks again, everyone, for joining us, and have a great one.
Yep. Thank you.
All right. Thanks.